Special course in mathematics, lecture 3, analysis. Let us start with recalling what a sequence of real numbers is. Definition: a sequence of real numbers is a map from the set of all positive integers to the set of all real numbers. And this is usually written as A1, A2, A3, and so on. So AI is the image of I under this map. For example, we have the sequence 1, 2, 3, 4, and so on. That's a sequence of real numbers. And we have the sequence 1, 1/2, 1/3, 1/4, and so on. That is also a sequence of real numbers. Here is a fancier sequence where the image of I, so the element AI, is equal to the sine function evaluated at I plus 1 factorial. Definition: a sequence A of real numbers is called bounded, provided that there is a real number capital B, such that the absolute value of all elements of our sequence, so of all AIs, is less than or equal to this B, for all I. And the sequence A is called unbounded if this condition is not satisfied. For example, the first of our example sequences, 1, 2, 3, and so on, is unbounded. And the second sequence, 1, 1/2, 1/3, and so on, is bounded. As a bound here we can take the real number 1. The absolute value of all elements in the sequence is less than or equal to 1. Also, our third example was an example of a bounded sequence. If we evaluate the sine function at any real number, we get a real number between -1 and 1. So the sequence sine of I plus 1 factorial is a bounded sequence. Now, here is our main theorem for today. This theorem is due to Euler and is taken from his paper from 1737. Let us write all prime numbers in the natural order. So P1 is the smallest prime number, P2 is the next one, P3 is the third prime number, and so on. Then the following sequence is unbounded. The first element of the sequence is 1. The second element is 1 plus 1 divided by P1. The third element is 1 plus 1 divided by P1 plus 1 divided by P2. And so on. So it's a sum of reciprocals of the prime numbers, of the first I prime numbers. And if we can prove this theorem, then we of course have as a natural corollary that there are infinitely many prime numbers. If there were only finitely many prime numbers, the sequence would become constant after a finite number of steps, so it cannot be unbounded. But the claim is that it is unbounded, and so there are infinitely many prime numbers. The reference from this theorem is Euler's paper from 1737, which is called Variae observationes circa series infinitas. Now let us prove this theorem. So let us assume that our sequence is bounded. So the sequence 1, then 1 plus 1 divided by P1, then 1 plus 1 divided by P1 plus 1 divided by P2, and so on, that this sequence is bounded. Then there exists a real number capital B, such that all terms of the sequence are less than or equal to B. Note that this is a sequence of positive real numbers, so it's enough to bound the elements of the sequence, the absolute value coincides with the element. Note that if we have some bound capital B, so some bound which satisfies this condition, all elements of the sequence are less than or equal to this capital B, then for any B prime which is bigger than B, B prime is also a bound. So if we have some bound, all bigger numbers are also bounds. On the other hand, if we have some real number B prime such that all B which are bigger than B prime are bounds, then B prime is also a bound. Therefore, we can take the set of all bounds of our sequence, and this set has a minimal element. So we can take as capital B the minimal possible bound for our sequence. And this is usually called the supremum of the sequence. Now note that our sequence is increasing or becomes constant after a finite number of steps. So 1 is smaller than 1 plus 1 divided by p1. This is smaller than 1 plus 1 divided by p1 plus 1 divided by p2, and so on. So we have our minimal possible bound capital B, so we can consider the real number b minus 1/2. And since our sequence is increasing, or eventually constant, and b is the minimal bound, so b minus 1/2 is not a bound, which means that all but finitely many elements in our sequence are strictly greater than b minus 1/2. In other words, there is a positive integer m such that 1 plus 1 divided by p1 plus and so on plus 1 divided by pm is less than or equal to b minus 1/2, and 1 plus 1 divided by p1 and so on 1 divided by pi is strictly greater than b minus 1/2 for all I that are greater than or equal to m plus 1. Great. Now we will use this fact in order to divide all primes into the so-called small and big primes. We will call the primes p1, p2 and so on pm small. So this m is this m. So the sum of reciprocals of all small prime numbers is less than or equal to b minus 1/2. And we will call primes pm plus 1, pm plus 2 and so on big primes. So now let us split all positive integers into two disjoint sets. The set X, which consists of all positive integers which have at least one big prime divisor. And the set Y, which consists of all positive integers whose all prime divisors are small. Clearly, directly by the definition, any positive integer is either in X or in Y, and the intersection of X and Y is empty. So the set of all positive integers is a disjoint union of X and Y. Okay, so how we will get a contradiction which will prove Euler's theorem? So let n be a positive integer. For this positive integer n, consider the set n over... For this positive integer n, consider the set n underlined, which is the set of all integers which are positive and between 1 and n. So that's the set 1, 2, 3 and so on up to n. Define x sub n as the intersection of x with n underlined, and y sub n as the intersection of y with n underlined. Of course, xn union with yn is n underlined, and xn intersection with yn is empty. So in particular, the cardinality of xn plus the cardinality of yn should be n. And we will show that for big enough n, this equality is not possible. In fact, we will show that for big enough n, both cardinalities of xn and yn are less than n divided by 2. Okay, first let us try to estimate the cardinality of xn. So claim the cardinality of xn is less than n divided by 2 for all n. Proof. Recall that xn is the set of all integers which have at least one big prime divisor. So for a fixed n, if we take the big prime pm plus 1, we have at most n divided by pm plus 1 numbers in the set n underlined which are divisible by pm plus 1. Similarly, we have at most n divided by pm plus 2 numbers in the set n underlined which are divisible by pm plus 2, and so on. So if some pi is greater than n, then there are no elements in n underlined divisible by pi. So therefore, for some element I, the cardinality yn is not greater than n divided by pm plus 1 plus n divided by pm plus 2 plus and so on plus n divided by pi. And if we take n out, we get n times 1 divided by pm plus 1 plus 1 divided by pm plus 2 plus and so on plus 1 divided by pi. However, this sum in brackets is smaller than 1/2 by our choice of m, because this sum is exactly the difference between two elements in our sequence, and by our choice of m and our definition of big primes, this is smaller than 1/2. And this proves our lemma. Now let us estimate the cardinality of yn. Lemma, we have that the cardinality of yn is smaller than n divided by 2 for all n which are greater than 2 to the power 2 times m plus 1. So m is the number of small primes. Proof: each element in y can be written in the form a times b square, where a is a product of different primes, and so there are no repetitions, there are no squares inside a. So you can write any positive integer as something which is not a square times a square. Since all prime divisors of R are small, the factor a can be chosen in 2 to the power m different ways. We have m small prime numbers. In a, each of them can appear with multiplicity either 0 or 1. So there are 2 to the power m choices. And if our element R belongs to yn, so if it is less than or equal to n, then the square part b can be chosen in at most square root of n different ways. B must be less than or equal to the square root of n. So therefore, the cardinality of yn is at most 2 to the power m times square root of n. And now we just need to solve the inequality. 2 to the power m times the square root of n is smaller than n divided by 2. And this is equivalent to the inequality 2 to the power m plus 1 smaller than the square root of n. And the latter is true if n is greater than 2 to the power 2 times m plus 1. And this completes the proof of this lemma. So for all n, the cardinality of xn is strictly smaller than n divided by 2, and for all n big enough, the cardinality of yn is strictly smaller than n divided by 2. This gives us the contradiction, which proves Euler's theorem, and hence, as a corollary, also Euclid's theorem. Let us now discuss another analytic proof of Euclid's theorem. For a positive integer n, let us define pi of n as the number of prime positive integers that are less than or equal to n. So here is an example of this function pi of n. So if n is equal to 1, then pi of n is 0. If n is equal to 2, then pi of n is 1. We have the prime 2. If n is equal to 3, then pi of n is 2. The primes are 2 and 3. If n is equal to 4, then pi of n is 2. The primes are 2 and 3. If n is equal to 5, the pi of n is 3. The primes are 2, 3, and 5, and so on. So for a positive real number x, recall that the natural logarithm of x is defined as the solution of the following equation. So the exponent of the natural logarithm of x is equal to x. Alternatively, we can define the natural logarithm of x as the integral from 1 to x of the function 1 divided by t, dt. In other words, the definition via integral of a positive function is the area between the graph of this function and the x-axis. So the logarithm is the area under the graph of the function 1 divided by t between 1 and x. And since this function 1 divided by t is decreasing, this area is of course greater than 1/2 plus 1 divided by 3 plus and so on plus 1 divided by the floor function of x. So the floor function of x is the maximal integer which is less than or equal to x. Lemma, the sequence 1/2, then 1/2 plus 1/3, then 1/2 plus 1/3 plus 1/4, and so on, is unbounded. Proof. We of course have that 1/3 is greater than 1/4, and so 1/3 plus 1/4 is greater than 1/4 plus 1/4, which is 1/2. Similarly, 1 divided by 5, 1 divided by 6, and 1 divided by 7 are greater than 1 divided by 8, and so the sum 1 divided by 5 plus 1 divided by 6 plus 1 divided by 7 plus 1 divided by 8 is greater than 4 times 1 divided by 8, which is 1/2, and so on. Therefore, 1/2 plus 1/3 plus and so on plus 1 divided by 2 to the power m is greater than or equal to m divided by 2, and this is of course unbounded. Consequently, the logarithm of a positive integer n is an unbounded sequence. On the other hand, again, since 1 divided by t is a decreasing sequence, the natural logarithm of n, that's the area under the function, it is smaller than 1 plus 1/2 plus 1/3 plus and so on plus 1 divided by n. Let Zn be the set of all positive integers whose all prime divisors are less than or equal to n. Then the logarithm of n is less than or equal to the sum k from 1 to n, 1 divided by k. And then, of course, if we have an integer between 1 and n, then all its prime divisors are less than or equal to n, so we can make this sum greater by summing 1 divided by k over all k in Zn. So Zn contains n underlined. Now let p1, p2, and so on, p pi of n be all primes that are less than or equal to n, which are written in the natural order. So every element in Zn has a unique factorization into a product of these primes. And therefore, this infinite sum over all k in Zn, 1 divided by k, can be written as a product, j between 1 and pi of n, and then the sum I greater than or equal to 0, 1 divided by the i's power of pj. And this factor, this infinite sum here in this product, it's a geometric series. So we can use the formula for the sum of the elements in a geometric series, and we write the product of this infinite sums as a product, j from 1 to pi of n, and then this sum is equal to 1 divided by 1 minus 1 divided by pj. Multiplying with pj, we will get pj divided by pj minus 1. So then we have a product over all j from 1 to pi of n. Of course, the j's prime pj is greater than or equal to j plus 1. Therefore, this factor pj divided by pj minus 1, we can rewrite it as 1 plus 1 divided by pj minus I. And this is less than or equal to, we can change pj to j plus 1. So it's a smaller number. So if we put it into the denominator, we get a bigger number. So that's less than or equal to 1 plus 1 divided by j. And this is j plus 1 divided by j. So we can now rewrite our product as a product over all j from 1 to pi of n, j plus 1 divided by j, and then everything cancels except for pi of n plus 1. And so if we now put all this together, then the natural logarithm of n is less than or equal to pi of n plus 1. And this means that pi of n is greater than or equal to the natural logarithm of n minus 1. But we saw that the natural logarithm of n is unbounded, therefore pi of n is also unbounded. And this gives us another analytic proof of Euclid's theorem. Some extra problems and questions at the end. Problem question 1. Let p1, p2, p3, and so on be all prime numbers ordered in the natural order. Prove that the sequence 1 divided by p1 plus 1 divided by p3 plus 1 divided by p5 and so on plus 1 divided by p2n minus 1 is unbounded. Problem question 2. Prove that the similar sequence, but now we take the sum of reciprocals of primes which are indexed by even numbers. This sequence is also unbounded. Problem question 3. More complicated situation. The sequence 1 divided by p1 plus p2 plus 1 divided by p2 plus p3 plus and so on plus 1 divided by pn minus 1 plus pn. This is unbounded. And yet more complicated sequence 1 divided by p1 plus p2 plus 1 divided by p3 plus p4 and so on, that this is also unbounded. And finally, problem question 5. Prove the formula for the sum of a geometric series. So for all real x whose absolute value is smaller than 1, prove that the sum over all I greater than or equal to 0 of x to the power I is equal to 1 divided by 1 minus x. Thank you very much and see you next time.